What's up, guys? In this video, what I want to do is work on a problem that's a little bit more challenging than your normal kind of solving trigonometric equations. A lot of times these types of problems will show up on a free response test and you'll be like, where did this just come from? But it's a good question, and everything that you know about trigonometric identities and solving trigonometric equations can still be applied in this problem. So the first thing I recognize is if I have the tangent of x plus secant of x, those are not like terms, right? So I cannot combine them. So kind of going into my thinking hat of thinking about identities, I'm just going to go ahead and rewrite these in terms of sines and cosines. So tangent, we know, is going to be a sine of x over a cosine of x. And then secant, I can rewrite as a 1 over a cosine of x. And that's equal to the square root of 3. All right, so now they have the same denominators. So I can rewrite the sine of x plus 1 all over a cosine of x equals the square root of 3. I want to get the sine, or this cosine of x, off the denominator. So what I'm going to do is I'll multiply a cosine of x on both sides. And now what that's going to do, that's going to divide over here. Now I'm going to left with a sine of x plus 1 equals a square root of 3 cosine of x. Now here's where it gets a little tricky, and something that we don't do a lot of in solving trigonometric equations, or at least probably you don't get a lot of examples with this. But one thing I recognize here is if I have a sine and a cosine, I want them to be the same, right? I want either to deal with all sines or with all cosines. Now the only way I can do that is by utilizing my Pythagorean identities. So I can convert between my sines and cosines when they are squared, but I don't have anything squared in this case. That's exactly what I'm going to do. I'm going to square both sides. Just like I went ahead and multiplied by a cosine of x on both sides, we can square both sides. Now again, remember when you have sine of x plus 1 squared, that's just going to be a sine of x plus 1 times a sine of x plus 1, right? So just go ahead and use your good old FOIL to multiply this out. And when you do that, you're going to get a sine squared of x plus 2 sine of x plus 1. That's a perfect square trinomial. And then over here, just make sure you square both of these. Since these are separated by multiplication, you can use the power to product rule. So what that's going to do is give you a 3 cosine squared of x. So now you recognize everything. You're like, all right, well, I have sine squared and cosine squared, but they're not the same, right? Well, again, that goes into your Pythagorean identities. If I know that sine squared of x plus cosine squared of x is equal to 1, I can rewrite a cosine as, or I can rewrite a cosine of x equals a 1 minus a sine squared of x, right? So if I go ahead and now substitute a cosine squared of x for a 1 plus sine squared of x, I can now go ahead and rewrite everything in terms of sine. Okay, and now what I can do is just go ahead and apply good old distributive property, and that's going to give me a 3 minus a 3 sine squared of x. Now all I'm going to do is get everything to the same side. So I'm going to subtract a 3 on both sides, and I'm going to add a 3 sine squared of x to both sides. And when I go ahead and do that, now my right-hand side is going to be equal to 0. And my right-hand side, I'm just going to simplify to this. Okay, now the reason why I divided out the 2 on both sides, because the 2 is just a scalar. It's actually not going to impact my solutions. If you think about that as a graphical approach, it's just going to be a vertically stretching the graph, but it's not actually changing the solutions. And notice when I added a 3 sine squared of x, I added that to the sine squared of x, right? Because those are like terms. That's how I got the 4 sine squared of x, and 1 minus 3 is going to equal -2. So now I recognize this equation, and hopefully you recognize that this is a quadratic equation. And remember, we can solve quadratic equations by factoring. That's why it's so important to have this equal to 0, because when you're solving by factoring, you're looking into factoring it and then applying the zero product property. Now, some students still get stuck with this because we have this coefficient of 2. So again, we can always go back to our lovely little trick here and just rewrite this quadratic in terms of x's. Now remember, whenever you have a quadratic trinomial, we can always rewrite this as a product of 2 binomials. So in this case, we can have something like this. And then again, to multiply my first 2 terms to get to 2x squared, I'm going to have a 2x and an x. To multiply my last 2 terms to give me a -1, that's going to be a positive 1 and a -1. Now I just need to determine where should I put those so they're going to add to give me a positive x. Well, in that case, what I want is this to be a positive 2, because 2x times 1 is a 2x. And then here is going to be the negative, because 2x plus -x is just going to be a positive x. So if I just go ahead and say, why don't we let x equals a sine of x? What I can do now is I can replace all these x's with a sine of x. That is an easy way to be able to factor a quadratic expression like this when you get confused with your trigonometric functions. Okay, so now we have a product equal to 0. And remember, when we have a product equal to 0, we can apply what we call the zero product property. We can set each factor equal to 0 and then go ahead and solve. Now, what's so helpful about this, especially in this example, is we can now use our inverse operations to solve for x. Now you see we solve for x for both of these equations. Sine of x equals 1/2 and sine of x equals -1/2. We are not done. We are looking for what x is. And again, what does x represent? X represents the angle that makes this equation true, right? The sine of what angle equals 1/2. The sine of what angle equals -1. And if you're thinking about the sine of an angle, especially if you're thinking about on the unit circle, then the sine of that angle represents the y coordinate of a point on the unit circle. Since we're trying to find the solutions between 0 and 2 pi, we're only going to look for the points on the unit circle where my y coordinate is either going to be a 1/2 or a -1. Those angles that produce that point are going to be our solutions. Let's go and draft up a quick little version of the unit circle and see what angles are going to produce these values. All right, so you can see in this example here, I have all where the y coordinate is positive 1/2, as well as when the y coordinate is -1. Now we just need to know, well, what exactly are these angles, right? And so hopefully you have some familiarity with the unit circle, and you can recognize that this angle in terms of radians is going to be a pi/6. This angle is still going to have a reference angle of pi/6, but it's pi/6 short of halfway around a circle, which is pi. So therefore, this angle is going to be a 5 pi/6. And its last answer, if you think about this in terms of halves, like this is half a pi, this is a full pi, then this is going to be 3 pi/2. And that is going to be your 3 solutions for this equation. That is going to be your solutions on the interval of 0 to 2 pi for this equation. I hope this video is helpful for you. If you want more examples easier, go ahead and check out the examples and resources I have for you down below. Otherwise, go ahead and take a look at the next video I have for you here.